So now we're going to go through another example of a graph reduction. So this one's a very straightforward problem that you might have even experienced before, where you have a bunch of cities and airlines between different cities, and your goal is to get from city A to city B. And essentially, in this problem, it's just like in general when you're driving from one city to another, except now instead of taking roads, you have multiple options for which flight you're going to take. So between the same two cities, maybe there's multiple different airlines that all have different prices. So in this problem, you have to both pick which airline you're going to choose and which particular overall path. So in this problem, it's easy. If you want to get from A to B, you have no choice but to go from this city to this city to this one. And this one also, you have no choice what to do. There's only one airline. But here you have to pick which airline would be best. And in this problem, we're allowed to actually switch airlines. So it's pretty convenient. So for example, we could start at A, take the bottom airline, which takes a flight cost of 6. We end up there. We take the only flight possible, which has flight cost 6, and so we end up at city B with total flight cost 12. So this is the first part of the problem. We'll solve this first, and it's pretty straightforward. The only complication is that we have multiple options. So let's model this as a graph problem. So we have V equals all the possible airports. So I said these were like cities, but for this problem, they're technically airports, all being in different cities. So V, we have a different vertex for each airport. And for simplicity, let's just say there's N airports, and we label them 1 to N. These are the labels. Okay, then the edges. Well, we're going to have an edge from I to J if airport I has any flight to airport J. And this will be a directed graph. And it's also a weighted graph. And now the main question is, what is the weight for any edge? So we're going to have the weight from I to J to be the flight cost, or specifically, we'll say the smallest flight cost. From I to J. So in our example above, this corresponds to just picking the smallest, picking basically the best airport or the best airline at that particular airport. So essentially, we're collapsing all of these three options into a single option, which is clearly the best one. So it's not super complicated to fix that complexity there. So then, now what's the problem? Well, it's just the normal shortest path problem. And how do we solve that? Well, because all of our weights here, we're assuming are positive, the cost of the flight's either time or money, and so, of course, it's going to take, you can't take negative time to get to your destination, and you're not going to get paid by the airline to take their flight. So we know weights are positive, or at least non-negative, so we can use Dijkstra. And remember, Dijkstra is the best general shortest path algorithm. If you have non-negative weights, you can use Dijkstra, which will be much faster than Bellman-Ford. Now, if you don't have cycles, you can use DP and it'll be even faster, but here, we're not going to assume there's no cycles. There very well should be cycles if we have enough airlines. Okay, so we use Dijkstra to compute the shortest path from A to B, And then what's the time? Well, this is going to be O of v plus e. And what's v plus e? Well, that's just O of n plus m. If we assume n is the number of airports and m is the collective number of airlines per airport, or at least an upper bound. Or we could just say total flights. Okay. So first problem, pretty easy. It's basically just the normal shortest path problem. We just had to tweak the input slightly because it's technically not a graph, so we just had to slightly modify it. But otherwise, it's pretty much just a normal shortest path problem. Now the second problem is a bit harder. Here, each airport uses different taxes. So just to enter the airport, it costs you some money. So now it might be better, say, to take a really bad flight. So maybe there was a direct flight that was super costly, because if you were to take the intermediate flight, the tax now makes it not worth it. So let's say this flight was cost 13, which is worse than 12, but now we have the additional tax of 5 to hit that airport. So it'd actually be better to just take the slower direct flight. And this problem's a little more complicated. So how are we going to represent this? So basically, nodes and edges have weights now. So we're going to use a trick. So let's say we had an edge u to v, and this had some cost like 5, 10, and 6. Well, we're going to split the node into a u in, a u out, and have the edge between them be 5. So we're still getting that 5 node cost. It's just now in an edge. Then we have our 10. This is v in. This is v out. And this has weight 6. So now if you took a path from u to v, or took the edge u to v, its cost in the first and original graph is equal to the edge cost of the path u in to v out in the new graph g prime. So we just take the node weights out and convert them into edge weights. And this preserves the total weights. So this means there's no difference. So now if we apply this to the graph we constructed before, then we're done. So just to spell it out, let's directly construct it. So v prime is going to be a set of v in for each v in the original graph, unioned with a v out for each v in the original graph. E prime is now going to be, we have a v in to v out. This is for all v in the graph. Then we also have, for each edge u to v, we'll have a u out goes to v in. That's for each edge u to v in the original graph. So that's just implementing this picture here into mathematics. We have the u out to v in edge. Then we have the u in to u out edge and the v in to v out edge. And And what will the weights be? So for this case, the weight of V in to V out is the airport tax at V. So remember, V is an airport, so that's just its tax. And the weight of U out to V in, this is just the weight of U to V from the original, which is again the cheapest flight from U to V. And at last, it's pretty clear, but we should still say it's directed. And it's weighted with these corresponding new weight functions, W prime. And now again, the problem is just shortest path. And the algorithm, again, will just be Dijkstra. And specifically, after we run Dijkstra, this will create a D function for every node starting from A. So we want to return D of B. That's our return. Okay. And finally, what's the analysis? Well, how long does it take us to construct this graph? Well, really, we're only doing twice as much work. So it takes twice as much time to double all the vertices, and we're just adding one edge per vertex, so at most M more work, or N more work if there's N airports. So overall, it's still going to be O of N plus M, because now we just have 2N is the size of V prime, and the size of E prime is going to be the original M plus an extra edge for each airport. And that's it.